Alright guys, so in this video we're going to go ahead and finish off the chapter. We're going to look at section 1.3, the history of AI, and section 1.4 is going to talk a little bit about the state of the art, and then we'll finish up with a brief summary. So section 1.3 from the text is going through and trying to give you a high-level overview of some of the major events of, or in AI that have occurred in AI over the past, 50 years or so, right? And so it's trying to give you a feel for what happened, what some of the major contributions were from each era, that sort of thing, right? So let's go ahead and go through it briefly, right? You're going to read through this, but I'll just go ahead and summarize it for you. So, gestation of AI, 1943 through 1955. Essentially, the first work related to AI that was recognized as AI was done during this period, right? So there's a couple of guys, Warren McCulloch and Walter Pitts, and what they tried to do is they tried to do some research, do some work related to physiology, human physiology, and neurons in the brain. Right? They also utilize propositional logic, which we're going to study, and they based their work off of Turing's theory of computation. So they were the first ones to try to basically tie a lot of these elements together to produce stuff related to AI, or generally referred to as AI. So way back when, right, it was 70 years ago, they were able to propose, based off of all this work they were doing, the first network of artificial neurons, leveraging their knowledge of human physiology and using propositional logic and Turing's theory of computation. And they were able to show that any function that was computable, right? So any function that a computer could work out, think about mathematical functions, that could be computed through a neural network, right? So they were talking about this. Neural networks were a known thing way back then, okay? So a guy named Donald Hebb showed how you can update neuron networks or neural networks by using what he was to become famous for, right? A rule that he came up with called the Hebbian rule, right? You don't have to know about it. If you're interested, feel free to Google it. Now, the first neural network computer, these guys were doing theoretical stuff. The first neural network computer was built in 1950. Okay, in 1950, so again, 70 years ago, there was a computer that was built based off of neural networks. And believe it or not, it was built by undergrads, right? And the name of the computer was the Snark. Now, here's the thing about being undergrads in computer science back in the 1950s. You're working on your PhD or something like that. Nothing had really been discovered yet, relatively speaking, right? It was a lot easier to get a PhD back then than it was to get a PhD now, right? I mean, back then they're like, oh, look, I came up with a new way of sorting an array. Ooh, I'll do a thesis on it, So, undergrads did some impressive stuff, but yeah, I mean, they were able to come up with the first neural network computer. I guess that is kind of impressive, though, right? So, maybe I misspoke a little bit. Now, Alan Turing, where we talked about him in previous video, he was going around giving lectures on artificial intelligence during this era, and as you can imagine, he had the most influence at that time. Okay, so 1956, the birth of AI. Essentially, there were a couple of big players at the time who were working in different fields. A guy named John McCarthy was working at Stanford, a guy named Claude Shannon, Nathaniel Rochester. They combined with Minsky, who we just talked about, and they proposed a meeting of the minds, as it were, in Stanford, or at Stanford. Or he was working at Stanford. I guess they got together, maybe it was at Carnegie Mellon. Whatever, I can't remember exactly where. But the big thing is that they got together and had a meeting of a bunch of really important people, movers and shakers, thinkers at the time in AI. And so what they said is they were like, okay, we're going to have this 2-month workshop, and at the end of this workshop, there's some goals that we're going to try to accomplish, right? So the workshop went off. They didn't accomplish everything that they set out to accomplish, but there were a couple of guys there who were the most impressive, right? Because these guys named Newell and Simon, they came up with a primitive reasoning program, right? So they came up with a program that they wrote that could do basic reasoning, right? So applying some logic and some of the rules that Aristotle and the other philosophers had laid down. So they were able to prove certain theorems, okay, and they claimed it solved this famous mind-body problem, right? So they made a claim, and the contribution here was, look, we have a computer that can prove stuff, okay, it can prove theorems. That was the big deal. And again, if you want to know about the mind-body problem, go ahead and Google it. I'm not going to ask you any questions about it on a test or anything like that. The big idea here is a bunch of important people got together, and they had a minor accomplishment here. They had an AI that could prove theorems, okay? But the other goals that they tried to accomplish, they didn't have any other really major breakthroughs, but the founding fathers, the forefathers of AI, they all got to know each other. And this workshop really is what established AI as its own field, right? This is its own separate area of study now. We have this thing called artificial intelligence. And it was borrowing from all these other fields, all these other disciplines, as we've been talking about before, mathematics, philosophy. But there was a distinct spin on it, right? It was within the context, right, within the framework of computer science. Okay. Now, early enthusiasm, 1952, 1969. Now, in this era, we had these influential thinkers coming together. We had a lot of people starting to do some really fun stuff with AI, and they were making some headway during this era. Most people at the time, contemporaries, were saying, well, computers can't do this, computers can't do that, you'll never get a computer to do this one thing. Well, the researchers, the people who were working on this stuff, they responded. They said, oh yeah, here you go. You said we can't do it. We just did it. You said we can't do B. We just did it. You said we can't do item C. Well, we just did it. Okay, so there were breakthroughs. People were like, we can do cool stuff. They said it could never be done. Well, we're doing it. And about this time in this era, researchers working in the field of AI, they were able to come up with programs that could learn, that had a rudimentary form of learning. So there were some advances being made here, and people were getting really high expectations. About the same time, the Lisp programming language, the Lisp processing programming language was invented, and it really became the dominant AI programming language. And you're going to have a couple of assignments that you'll do just to give you a little bit of exposure with Lisp, right? This isn't a class on Lisp programming. You're not going to become experts or anything like that. I'll give you some tutorials, a couple simple homework problems, because I'm supposed to introduce you to Lisp or Scheme in the class. So, we'll give you a little taste of it, right? It won't be anything that you can't handle, though. Okay. So, a paper was published at the time called Programs with Common Sense, and that thing described the very first complete AI system, right? So there's a peer-reviewed paper published, said, okay, this is what it means to be artificially intelligent, okay? And so the system that they described was able to use knowledge, and using that knowledge, it was able to search and find solutions for problems. Okay, you could give this system new axioms. Remember what an axiom is? It's just a fundamental fact, basically. And what that meant was it could learn, it could evolve, it could get smarter, it could get better, it could become more intelligent without having to reprogram the whole thing from scratch, without having a human having to come in and reprogram the thing, recompile or whatever. Okay, so during this era also, the work with logic continues advancing, but specific to computers, right? I mean, you had logic in terms of philosophy and all that kind of stuff, What is God? What does it mean to be human? I think, therefore, right? That's all philosophical stuff, right? Now, computer science, especially in AI, borrows from that a ton. But in this era, they were applying more and more of the idea of logic, some of these philosophical ideas to computers, or within the context of computer science, artificial intelligence. Okay, additional work on neural networks is being done at this point. And then somewhere between 1966 and 1973, during this era, hit a wall. Okay, there was a dose of reality early on. I guess you could think of it as the law of diminishing returns, right? When you first discover something, when you're first learning something, you can make advances in leaps and bounds. But once you've picked all the low-hanging fruit, stuff starts to get a little bit tougher, right? Advances come slower. The acquisition of knowledge isn't as fast as it was when you first start learning about something. So some of those early predictions that they made in the previous era, where they're like, oh, well, we're going to be able to build a computer that can beat a chess champion in 10 years. Well, it didn't happen, right? It actually took 40. And they were running into problems with their programming that didn't utilize knowledge as they thought they could, right? So, for example, the textbook tells a story about how, during the Cold War, the national security apparatus was trying to use artificial intelligence, a form of artificial intelligence, to translate, secret Russian documents into English. And they were just doing basic things. They were thinking, oh, well, das vidanya means goodbye, or niet means no, that kind of thing, right? And so they thought, well, we could just do search and replace, essentially. Well, that doesn't work, right? You can't just do a search and replace for Russian words and for what their exact definition is in English, because the languages don't work like that, right? There's turns of phrases, there's colloquialisms. I mean, the translation isn't that simple. So the early programs relied purely on these manipulations of syntax, and you can't translate languages that way. It's a lot more complicated. So failed. Right? So they thought they could do it, it didn't work out. And some of the other walls that they hit here, some of the other problems that they encountered, was that some of the problems they were trying to solve, they were just too complicated. Right? So the early successes that they had, the problems that they were dealing with, were relatively simple to solve. Right? The problem spaces, as it were, what you're trying to deal with, small, simple, really easy to solve problems, right? Maybe 4 steps to solve a problem, 10 steps to solve a problem. Okay, now they're trying to solve problems that might take, I'm just giving that as a metric just to give you an idea of scale, maybe 10,000 steps, 200,000 steps, something like that. Okay, so basically the problem that they were running into was that the power of the computers at the time, not sufficient, right? There was a limit, hardware limit, essentially. So there's a quote from the textbook that says that a fact that a program can find a solution in principle doesn't mean it contains any of the mechanisms needed to find it in practice. So what that means is you can write the program that might be able to solve the problem, but if you don't have the hardware to run that program fast enough, you ain't solving anything, right? Because you'll be dead before the program spits out the answer. Okay, so a lot of those problems, way too complicated. Okay, so what this led to was an effort to divide and conquer, right? So if you can take a really complex problem, something that's really, really, really complicated, and you can break it down into smaller sub-problems, think like recursion, for example, right? Then you can have the computers maybe running in parallel that are working on each one of those sub-problems at the same time. And then when they're all finished, you have your overall solution. So there was a movement in that direction. Okay, so at this point, they come up with this idea of genetic algorithms. Okay, and a genetic algorithm is a way of subdividing problems. Okay, and these are my favorite subject in AI, because basically what they did was they leveraged the idea of biological evolution to solve complex problems, right? Because with evolution, the whole mechanism, the algorithm for how biological evolution works is really simple. You have some kind of mutation. If it's beneficial, that leads you to more likely reproduce than you otherwise would, right? And so then that change gets propagated to the next generation. Well, genetic algorithms borrowed from this idea. A series of small mutations leads to an optimal program. That's the big idea. Okay, so another problem that they ran into was that neural networks, right? This had to go back and do with neural networks. Is that theoretically they could learn, right? A neural network was able to learn stuff. They could learn anything they were capable of representing, right? The knowledge that they could represent, they could learn, right? Think about if you can picture it, you can learn about it, right? The problem is that neural networks at the time, they couldn't picture a whole lot, right? They were pretty limited in that regard. All right, so moving on. Knowledge-based systems, 69 through 79, that decade. So up to this point, AI research produced what's known as weak methods, and what that basically meant was that the sophistication of what they were doing wasn't that great. Okay, so you had search mechanisms that were used to search for solutions to certain problems, and what you did was you would string together a bunch of simple facts to get your solution, right? A leads to B, leads to C, leads to D, and therefore your solution, right? So for small problems, okay, you can make that work, right? Another example would be, if you're navigating a maze, turn left, turn right, go straight, turn left, go right, turn right, go straight, back up, whatever, right? Cool. It's not a whole lot of complexity there. But for bigger problems, it's a bit tougher. So what they tried to do, or some of the advances that they had in this era, was that they wanted to narrow the focus. Okay, we want to have domain-specific knowledge in our searches for solutions. Okay, so basically, what happened is that they were able to come up with new ways of classifying information. Okay, an example from the textbook goes to molecular analysis. I guess they had a machine, and this machine was supposed to be able to analyze certain molecules, and there's different signatures for different molecules, right? And you can think about essentially linear search versus binary search on a binary search tree, right? Linear search on a linked list versus a binary search on a binary search tree, right? If you had to go through every single item in a list, right, in a linked list, it could take a long time. So you can imagine that every node represents a particular configuration of these markers for a particular molecule. And so if you wanted to identify the molecule, you basically were like saying, is this the one I want? Nah. Is this the one I want? Nah. Is this the one I want? Nah. Is this the one I want? No. And there's tons of these molecules, right? So what they discovered, or what they came up with, was this idea that, look, there are different subgroups of molecules, right, that have, maybe a molecule has, I can't remember the exact number, maybe it has 20 markers on it or something, right? Think about it like a bar graph. Okay, and a certain subgroup, a certain family of molecules might have 3 markers that are configured in a certain way, right? So don't start your search out by looking for the exact molecule. Start with those 3 markers, right? And then search through that subgroup. So essentially what this allowed them to do, or the main advancement here, was the ability to classify information based on different factors, which would speed up the searches, because like the difference between a binary search tree and a linked list, you can search through subtrees of information as opposed to the entire domain, right? So you can search through subdomains of knowledge instead of the entire domain. Okay. All right. So what was the result of this? The first successful knowledge-intensive systems, right? Because they were able to take domains of knowledge and then break them up into subdomains. And then you only search through the subdomains that could have the information that you're looking for. Okay, next up, expert systems. And you're going to get a chance to make an expert system in this class towards the end of the semester. So expert systems were born really out of the first attempts were to come up with automated systems for doing medical diagnostics, I guess you could say, right? So there's the MySyn system. Essentially what happened is that this system, they built it to try to diagnose various blood disorders. Okay, and they came up with a set of rules, 450 rules, right, that had to do with describing these blood orders, essentially, or disorders. Okay, and they came up with these rules by doing a bunch of interviews with experts, doctors, PhDs in blood science, bloodology, whatever, and they got a pretty good idea for the types of disease, the domain of knowledge that they were having to write an AI for. They had to factor in some uncertainty, right? Because sometimes you ask a patient, well, how long has this been happening? I don't know, maybe a couple days, or there's a 70% chance that we think it's this, only 30% of patients exhibit this symptom, that kind of thing, right? So there was expert interviews that went into building this system. There was building in probabilities, right? Going back and leveraging mathematics, right, to be able to utilize probabilities for those kind of situations that I just described. And if you're building a system, an expert system that is diagnosing human beings, then that system has to be able to process natural language, right? Because you're describing, symptoms, certain aspects of the blood disease and what have you. And so the artificial intelligence needs to be able to process that human language that's describing those things, those facts, those rules. If your blood is green, you're terminal. Stuff like that, or green blood bad. Right. So anyway, once they finished building this thing, okay, they had to build in the natural language processing capability, probabilities, all of the knowledge in the domain from all the experts they talked to. Turns out that the system they built could diagnose a lot of the blood disorders as well as, a junior doctor, right? Maybe not a doctor that's been doing this for 30 years, but certainly someone who's been doing it for a couple of years, right? And sometimes, depending on the disease and the situation, the patient, as good as the best doctors there were, right? So that was pretty darn exciting, because they were able to say, well, look, this is going to be the big thing. We don't have to have doctors anymore. We can just have these systems that can diagnose everything. Well, as you know, if you've tried to use troubleshooter in Windows whenever something doesn't work, you can imagine how well that turned out, right? It was exciting when they first came up with it, but it's not the best. It's not going to replace human experts anytime soon. Okay, anyway, so this approach led to a development of logic-based languages such as Prolog, another language which you'll get some exposure to. Right? It's not a class in Prolog. I'm going to give you some tutorials. I'm going to give you some simple, a couple of really quick, really brief assignments to do with it that uses Prolog, just so you can get your feet wet with it, just so you can get a taste for it. Right, so it won't be nothing that you can't handle. All right, so 1980 to the present day, AI becomes an industry. Commercial expert systems are being built. Right? They come online in 1982, hugely successful initially. So as a result, all big corporations are like, oh, AI is the next big thing. We're going to have a group dedicated to developing artificial intelligence for supporting whatever work that we're doing. Japan takes the lead at this point. In 1981, they come up with this fifth generation, their so-called fifth generation project, and they're trying to build intelligent computers based off of Prolog, right, or using the Prolog language. US, of course, has to form a response. They come up with their own project known as the MCC project. Now, both of these groups, they never really met their goals, what they were trying to do, okay? But at the time, AI was booming. It became a multi-billion-dollar industry. People were like, "Oh, this is awesome! These expert systems are great." It didn't. Even though these groups didn't really hit all of their lofty goals, it still drove a pretty extensive industry. Right? So companies are building their own expert systems to varying levels of success. Robots are coming online. As you can imagine, there's hardware and software that's specially designed for AI. But at a certain point, like I was saying a second ago, these groups, they didn't hit their lofty goals, right? And after a certain amount of time, the industry kind of hit a wall, right? Where people were like, oh, well, AI, well, that was really cool. There was a lot of hype that was driving it, kind of like the dot-com era. And so a lot of companies that were investing in AI, well, they closed down. Okay, then from 1986 to the present, the return of neural networks. Neural networks are a big deal again. So it's kind of funny because in the mid-'80s, 4 different groups essentially reinvented algorithms that were discovered way back in 1969. Nobody would have been talking about neural networks for the longest time because of some of the problems that were encountered when working with neural networks that we talked about a few minutes ago. Right? So some of these algorithms, these learning algorithms that are related to neural networks are rediscovered and re-implemented, and there was some success. Applying these neural network algorithms, or these neural algorithms, I guess you could say, to certain problems related to computer science, psychology, and these successes became known as essentially the connectionist models of intelligent systems. Okay, I'll go ahead and leave it to you to skim through that. Again, Google it if you want to. The big idea here isn't, oh, I got to memorize the definition of connectionist models. No, the big idea is, look, neural networks have made a huge comeback. Okay. All right. So the debate reemerges. How do humans think? Or do they think symbolically or not? And the debate was raging on. Right? So the current view is that, and there came 2 basic broad camps, 2 approaches to thinking about this. One was the connectionist, and one was the symbolic. Right? Are you thinking in terms of symbols, or is thinking about connecting connections in your brain, like neural networks, etc.? The current view is that they're kind of complementary. Right? They, sometimes you think a little bit of symbols, sometimes you use a little bit of. Right, so there wasn't really one proved to be better than the other, and they're kind of like, well, we don't have to throw these 2 approaches aside, right? We can work with them together to get the best effect, I guess you could say. Okay, so modern neural network researching, you've got a field that's dealing with network architectures. I guess you could say that supports maybe more the connectionist people. And then you've got the other that's actually dealing with modeling, neurons. Okay. So big idea again is neural networks back. There's competing views as to how stuff works, but they're working together. Okay. 1987 to present. Now the big idea here is that before this era, the approach to studying AI was really kind of done in a scattershot kind of way, right? There was, some people over here were trying stuff, some people over here were trying stuff, just throwing stuff at the wall to see what stick. There wasn't a real organized approach to studying it, not really, okay? There were people who were trying to get people interested and working on it. We talked about the group that met, of all the big wigs when AI started, but everyone was kind of off doing their own thing. Okay, well, modern work basically has become a lot more scientific. Okay, AI adopts the scientific method. And what's the scientific method? Remember, make a hypothesis, a falsifiable hypothesis, come up with some way to falsify or come up with some tests that are falsifiable, and then test it. Publish your work, have other people, try to reproduce your results. Okay, that's kind of what's happening now, right? The methodology for developing stuff in AI, for developing new technologies in AI, is following this method now. It's pretty much a systematic approach to studying AI, even in the different subfields, right? People are coming up with new ideas. They got their hypotheses. They come up with their tests. They're publishing their work for review, etc. Whereas before it was kind of like random scattershot, like I was saying. Now it's following more, a scientific methodology. Okay, let's see, what else do I want to say here? Scientific method was applied to speech recognition and machine translation. That's also following the scientific method, and it's dominating the field. Neural networks, again, same kind of thing, used extensively. Neural networks, now they're pretty much dominating the idea of data mining, right? Working with big data. Bayesian networks are really evolving at this time, and those are important because they allow you to chain together uncertainties to make yourself a decision, right? If you have a 90% chance of this happening, and then that leads to an 80% chance of this happening, then that leads to a 30% chance of this happening, should I do it, kind of thing, right? And so these allow for the ideas of these so-called normative expert systems. Again, examples being troubleshooting tools, and so on, right? So similar stuff is going on at the same time with robotics, computer vision, knowledge representation. Again, systematic scientific method approach or scientific approach to studying these ideas in AI, right? It's all kind of converging, saying, okay, let's do this in a professional, systematic way. The emergence of intelligent agents, and that's what we're going to be focusing on, right? 1995 to present. Agents have really been the focus now, right? That's really where AI is putting its energy, and that's what this textbook is really about: is creating intelligent agents and how they interact with their environment, and the different ways that you can have them make decisions. So with agents, the reason why that this regained focus this focus has reemerged is because the application for intelligent agents is huge, right? So search engines, recommendation systems, website aggregators, right? So anything you can think of, cars that can drive themselves, right? Anything you can think of that can perceive that needs to perceive its environment, make decisions, and then act upon its environment. This is the realm of intelligent agents. It's pretty much everything. Okay, and you talk about something being able to learn, something being able to make decisions given there's uncertainty in its environment. Everything that we've talked about so far from these different fields, right, plays into supporting the development of these intelligent agents. Robotics, vision, the ability to represent knowledge, the ability to reason, to work through a logical process. These all come into building a successful intelligent agent. So since everything's kind of coalescing around building agents, you have all these different disciplines that are contributing or being drawn upon. And so the close proximity of these different fields all working together naturally leads to cross-fertilization of ideas, right? So now philosophy and robotics maybe are starting to exchange information, or maybe logic and vision, okay, artificial intelligence in terms of vision are starting to share ideas, that sort of thing. Okay, all under the umbrella of artificial intelligence. Okay, and lately the discussions have been revolving more and more, or coming up again, about trying to come up with a human level AI. And a related subfield of that is, look, if you're going to have something that has an intelligence that is that rises to the level of a human being, right? One of the things that characterizes human intelligence is the ability to learn, right? We can learn anything, okay? So there are people who are studying who are trying to make the argument and say, well, look, maybe we shouldn't be focusing on programming a particular artificial intelligence for a particular domain, self-driving car, or something that does stock trading, right? Instead of having a specific, tailored, customized UI for that or this, maybe what we should be doing is coming up with algorithms that just teach machines or artifacts to learn. And so then you run that learning algorithm, and then you tell the machine, you say, okay, learn how to trade stocks, learn how to drive a car, learn how to play music, right? And so people are saying, well, maybe that's where we should be focusing our energy. Maybe we should be saying, let's teach machines how to learn, then just tell them what to learn on their own. That'll be easier, right? So there's debate that's raging back and forth if that's the way to go or not. So if a machine can learn, if a machine can learn on its own, or if you can say, hey, I've taught you how to learn, now go learn what you need to do. What if that machine learns that it needs to kill humans, right? What if that machine takes a look at climate change or nuclear weapons or something and says, whoa, this is bad. I need to learn how to shut this stuff down. Maybe humans are the problem here. I need to eliminate humans. People have talked about that, right? Judgment Day, dun 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 dun. Come with me if you want to live. I'll be back. So serious thinkers are now starting to talk about, hey, you know what? We better make sure that these machines we're building are friendly. Asimov and his laws of robotics, right? So another thing that's coming up, right? We're almost done here. Another thing that's coming up around this time, 2001 to present, is computer science in general. Hope you've probably realized this by now if you're in this course. Computer science isn't about learning how to program. It's not learning about how many bytes there are in an integer variable or how to make a for loop in Python. It's not about that. That's kid stuff, right? That's just learning how to swing a hammer. Okay, computer science really focuses on the science of making things work, right? It's more about studying algorithms. That's where the emphasis is. Because you take class analysis of algorithms. Why do you do that? Because you want to come up with ways to solve problems in the most efficient way. That's where it's at. It's all about the algorithms. Okay, now, serious thinkers in the realm of artificial intelligence said, wait a minute, maybe we should shift some of that focus. Maybe we should stop focusing so much on the algorithms, and maybe we should put a little bit more emphasis on the data, because there's huge amounts of data out there now, right? Ginormous amounts. The United States government has a storage facility. I think it's in Colorado. I mean, you can look this up. It's public domain. I'm not, making anything up here. Where they record every single keystroke that has ever been made on, Microsoft products, for example. Right. So all that stuff's being saved there. Every email that goes between the United States and the European Union, a copy of it gets saved somewhere. Right, so there's a tremendous amount of data. Think about all the crap you give to Facebook for free. Right? Think about all the tweets that you make. Think about everything that you've done related to Google, all your Google searches. Google warehouses all that information. Okay, so the idea here is, look, if we can come up with an algorithm where we can give an AI a small initial set of data to work with, right? So on the slide, say a small set of words. Then the AI can use that small set of information to come up with new descriptions or new ways, new rules for how to use words in a sentence. So I can give a computer, say, maybe we can give a computer a small vocabulary, and then it can figure out how to combine those words into all kinds of different sentences. Maybe we give it 100 words in like 3 sentences. And then the AI figures out, well, hey, based off of that, based off of how the structure, the grammar of those sentences and these words, well, I can reconfigure all these words into different sentences or come up with new sentences, right? That's the idea. Or another example, and this is something Facebook does. One of the reasons they love you to upload your photos is because they're working on perfecting their facial recognition software, right? So, you start off with a small set of pictures, okay, and 10,000 pictures or so, and once you have that small set of pictures, could be that another picture comes along that's incomplete, like, I don't know, maybe a picture of a protester with his face covered by a mask, okay, and based off of those initial 10,000 photos that you had, maybe courtesy Facebook or what have you, you can figure out, you can fill in the missing parts of the protester's face, or maybe it's a little bit more benign. Let's not get all conspiracy theory here, right? Maybe you just have a picture that you're trying to restore of a great grandfather or something, right? So based off of a huge set of human faces, you can reconstruct that incomplete photograph. Okay, so the idea here, again, going back and saying, look, the problem isn't hard coding specific artificial intelligence for specific problems. The idea is, let's teach a machine the basics of something and how to learn, and then just tear it loose. Right? Could be scary. All right, so I said that I was going to do 1.4 in this video too, but I feel like this video has gone on long enough, so I'll go ahead and end it here, and in the next video we'll finish off, right? That'll be a short one, and then we'll be done with chapter 1, right? And then you'll be able to head on and get started on your homework assignment and all that, and get your quiz going, okay? All right.